Welcome to the session on detecting fraud with Amazon SageMaker featuring Coinbase. My name is Soji and I'm a machine learning engineer at AWS. Joining me in this presentation is Eric, an engineering manager at Coinbase, who is going to shed some light on how Coinbase is leveraging AWS and SageMaker to build their fraud prevention systems. We hope this session will inspire you to take the next steps to start realizing the benefits of using machine learning for fraud detection in your business. Let's take a quick look at some of the topics we will be covering. I will go over how machine learning, or ML, can address some limitations with traditional fraud detection methods. Then I will give an overview of the features of Amazon SageMaker that will enable you build and deploy highly performant fraud detection models for your business. Then Eric will give you a deep dive into the machine learning fraud detection framework at Coinbase and how they were able to build a framework that met their strict requirements by building with AWS and Amazon SageMaker. Finally, I will share with you an exciting way for you to get started building your own fraud detection solutions by describing two machine learning solution templates provided by Amazon SageMaker. These templates demonstrate how to train SageMaker models for fraud and how to deploy or use these trained models in a highly scalable architecture. Actually, let's start right there. The fastest way to get a fraud detection system up and running on SageMaker is to use the Amazon SageMaker solutions. Our solutions are templates which help you get started in minutes. You can launch all the SageMaker and AWS components for a fraud detection system right away without having to worry about wiring components, and you can get a prototype running in no time. The solution provides the necessary components to build an end-to-end system, including Jupyter notebooks to show data processing and model training, demo endpoints to show how the trained models can be invoked to get predictions, and other AWS components for packaging the solution into a REST API and or for performing post-hoc analysis or dashboarding. You can find more information about the solutions on the SageMaker Getting Started page. Later on, we will go into some details about each of the fraud solutions. But first, I will go over some reasons why machine learning is a compelling way to tackle fraud detection and highlight some of the features of Amazon SageMaker that reduces the complexity of building and deploying machine learning solutions. So a traditional way of combating fraud is to use rule-based fraud detection systems. Rule-based systems are generally a static set of rules created by human experts. These rules are typically generated to filter out known outlier events or fraudulent behavior. These rules are usually business-driven and they are often derived by performing post-hoc analytics and deep dives on known fraudulent cases and relying on human intuition to observe fraudulent patterns. For example, in deciding whether to accept a credit card transaction as legitimate or fraudulent, the rule-based system has checks on whether the credit card is over limit or whether it has a high rate or it was reported stolen and so on. Right? Each of these individual checks may be enough to block a transaction, or a specific combination of field checks may actually be required. The rule-based techniques can actually be effective at preventing fraud. This approach also has some limitations. One limitation of rule-based methods is that the implemented rules are static. This means that they may not generalize well, especially to unobserved types of fraudulent events. Or in a different sense, the rule-based system is always reactive to some potential new kind of fraud, which implies there's a kind of catch-up game. As alluded to earlier, a rule-based system can have really complicated nested conditions and logic where you're chaining along lines of ifs and ors and elses. Right? So when it comes time to scale the system, right, for example, when there are new business avenues, the system scales poorly because the changes to the rule-based systems are always accumulative. On the other hand, machine learning can alleviate some of these issues with the rule-based systems. Right? So with machine learning, we train models on existing data, with or without labels, to automatically extract patterns that are associated with fraudulent or anomalous behavior. Right? So if we're training with labels, that is in a supervised setting, we can also hold out a portion of the label data to ensure that our model is dynamic and generalizes to data that is unseen during training. In addition, we can provide real-time feedback to the model for cases where the model made some erroneous predictions, right? And we can ensure that the model is updated with the correct response that is identified downstream. This means that model-based techniques for fraud detections are relatively easier to maintain as the size of the business grows, and they can scale quite well. So AWS provides choice and flexibility for our customers that are implementing machine learning based fraud detection solutions on the platform. Right. So for example, if you're building a fraud detection system and you don't have machine learning experience and you want to use a simple set of APIs that you can invoke to screen events or transactions, then you can use Amazon Fraud Detector. So Amazon Fraud Detector uses Amazon's more than 20 years of fraud detection experience to help customers catch more online fraud faster. Right. But on the other hand, if you have some machine learning experience or a team of data scientists working on fraud, or you want to experiment with like a couple options for building your own proprietary fraud detection models, then you can use Amazon SageMaker. Amazon SageMaker is a fully managed machine learning service that provides you with the flexibility for how you train your own fraud detection models. For the rest of the presentation, we will focus on how you can use SageMaker for fraud detection. So an easy way to get started with Amazon SageMaker for building fraud detection models is by using SageMaker Autopilot. SageMaker Autopilot is an easy-to-use and transparent AutoML system for various prediction tasks. AutoML stands for Automatic Machine Learning, and this means that using just a single line of code, SageMaker Autopilot will automatically perform feature extraction on your dataset, select several machine learning models, train those models, and then tune the model hyperparameters. You can also leverage some of the built-in machine learning algorithms that SageMaker provides to create a fraud detection model. SageMaker has a growing list of built-in algorithms for supervised learning, unsupervised learning, clustering, and others. Right? And this can work quite well for fraud detection use cases. So with a little bit of machine learning experience, you can even combine the predictions from different SageMaker building models for stronger ensemble predictions. Right? For example, if you have just partially labeled data, you can use IP insights for flagging malicious IP addresses, XGBoost for a supervised fraud prediction model, and random cut forest for an unsupervised fraud prediction model. Now, these 1P algorithms are designed to be used at Amazon scale. If you have significant machine learning experience or a team of data scientists and you want to implement cutting-edge deep learning-based models or use your own internal IP for modeling, you can still build those models with SageMaker. So SageMaker supports the leading deep learning frameworks like PyTorch, TensorFlow, and Apache MXNet for building neural network models using deep learning. You can also use scikit-learn, XGBoost, and SparkML as they are supported frameworks for machine learning on SageMaker. SageMaker also supports Deep Graph Library for training graph neural network models that directly take advantage of structural patterns in interaction graphs for fraud detection. And SageMaker provides all of this functionality as part of the SageMaker Python SDK, right? And this is a standalone ML library that is available by default on SageMaker notebooks. So finally, there are hundreds of pre-built models available in the AWS marketplace that can be used on Amazon SageMaker, including many fraud-specific models. These models are built by vendors and then provided on the marketplace to make it easy for you to get access to them. So with all these different ways of building a fraud model, SageMaker provides flexibility to customers and offers features that make the traditionally complex, expensive, and iterative process of machine learning accessible to all developers. So to interact with all of the different machine learning components and features under SageMaker, we provide a fully integrated machine learning IDE experience with Amazon SageMaker Studio. Right. With Studio, you can create new notebooks, train and tune models, adjust experiments, compare results, and deploy models to production all in one place. And with Studio notebooks, you can spin up one-click Jupyter notebooks that have fully elastic underlying compute resources, and they are designed for rapid prototyping. Also, SageMaker experiments help you organize and track iterations of your machine learning models. As you develop and prototype models, you will likely have multiple iterations of model training, which can lead to you producing a ton of artifacts, right? And so these iterations can be logged by SageMaker experiments, and then using the visual interface of SageMaker Studio, you can browse, review, and compare your various machine learning experiments. And once your fraud detection model is trained and deployed to a model endpoint, SageMaker still provides features to ensure that your model continues to produce high-quality predictions. Right? So to identify issues quickly in production and take corrective actions such as auditing or retraining the models, you can use SageMaker Model Monitor, which monitors incoming requests and your model's response and then can alert you when there are deviations in model quality. In addition, Amazon SageMaker Augmented AI, or A2I, makes it easy to build workflows for human review of ML predictions. With fraud detection, false positives can be disruptive to legitimate customers. So it actually is often a good idea to have human reviewers reviewing low-confidence model predictions. Right? So using Amazon A2I, you can allow human reviewers step in when a model is unable to make a high-confidence prediction, or you can have humans audit predictions on an ongoing basis. So now that you've seen a general picture of how SageMaker provides the functionality and flexibility for you to build your machine learning-based fraud detection systems, I will hand over to Eric to provide some details on how Coinbase built their implementation of a fraud detection system.
Thanks, Soji. My name is Eric, and I'll be talking about how Coinbase uses SageMaker and AWS to build our fraud prevention system. First, a little bit about Coinbase. Coinbase is on a mission to create an open financial system for the world. We have two main priorities: to be the most trusted and the easiest to use platform for cryptocurrency. We have over 35 million verified accounts and have done more than $320 billion in trading volume since our launch in 2012. We offer a variety of products for both institutional and retail customers across a variety of domains. As Soji said, fraud for online businesses is increasing. This is especially difficult with Coinbase. Coinbase attracts the most sophisticated attackers with the highest stakes. This is due to the nature of blockchain. Blockchains are immutable, and so if a fraudster manages to leave site with user funds, we have limited recourse in retrieving those funds. This directly violates our mandate of being the most trusted exchange, one of our main priorities. We use a variety of techniques for combating fraud at Coinbase. First, we have our risk analysts. These are highly skilled specialists in fraud prevention who use internal tools to track and assess clusters of fraudulent users. Next, we have our rules engine, an online system for applying rules against transactions and users, where the rules are developed by our analysts. And finally, we have our ML models. These machine learning models are developed in-house in order to automatically detect fraud happening at both the user and the transaction level. These three systems together have contributed to us reducing our fraud rate by 50% between 2018 and 2019. Today we'll talk about the platform that allowed us to build some of these state-of-the-art ML models. Here are a few of the models that we've built. We have our user risk model, our transfer risk model, our credit risk model, and our account takeover model. All of these models are highly sophisticated ensembles of both gradient-boosted trees via CapBoost and transformers using PyTorch for combining tabular and sequence-based modeling techniques. Our user risk model analyzes how risky we think an individual user is. Transfer risk assesses transfers, credit risk analyzes the credit we can give a user, and our account takeover model detects account takeovers in real time to protect users and their funds. Let's talk a little bit about how Coinbase develops machine learning models and the requirements that we have of our platform. We follow a model development lifecycle that looks like this. First, we prototype, then we productionize, then we experiment. Prototyping answers the question, can this problem be solved? How well can it be solved? What metrics do we care about? And how should we solve this problem? Typically, this is done in Jupyter notebooks because we need very interactive workflows with high resources in order to crunch a lot of data. Next, we productionize. This is about formalizing a prototype and making it work under production conditions such as high traffic and high load. We also want to ensure the reproducibility, and we also want to ensure reproducibility so that our online data is representative of our training data. Finally, there's experimentation. We roll out A/B tests for all of our models so that we can understand the performance of the models relative to their control. We use key business metrics and model metrics to measure both the impact on the business and the impact compared to how we and and the performance relative to how we thought it would perform. We additionally had three additional requirements when developing our ML platform. First, we needed our platform to be secure. We wanted to limit who can access it. We wanted to ensure that we wouldn't have any unreviewed code in production, and we wanted to have consensus mechanisms to guard against bad actors. Second, we needed it to be low latency. Our ML models are in critical path for many user workflows, and so we require SLAs as low as 80 milliseconds end to end. This includes retrieving the feature vector, scoring against the model, and returning a response to the service. Data must be as up-to-date as possible because sophisticated attackers know the site well and can move through very quickly or use clickbots. This results in us wanting transactional guarantees for some of the features that we use for our models. We also wanted our platform to be flexible. We believe that there is an advantage in using bleeding edge tech, and so we want to incorporate research into production as quickly as possible to solve our problems. We also want it to be low friction to add a new type of model to production. For example, and we also didn't want to be tied to any singular modeling framework. For example, when we moved from XGBoost to CatBoost, we basically for free got a 4% increase in the AUC of our model. Basically, we want to be able to deploy any model we need to solve problems within our business. So in summary, we needed a platform that was secure, low latency, and flexible, and fit the workflow that our MLEs need. Here's what we built. First, for prototyping, we used Jupyter notebooks provided by Amazon SageMaker. Notebooks are provisioned via our UI control plane, Nostradamus, and we codify all the configuration of notebooks. This ensures that all notebooks are secure by default and are properly peered with our VPC. We also have tight access policies for our S3 buckets that store our data, again, being codified and requiring +1s through consensus in order to make modifications. After provisioning a notebook, ML engineers can access notebooks via IAM roles in the SageMaker console. We use SSO in order to grant these roles and for users to log in. Next, we go to productionizing our models. Our models need to have a consistent shape so that our platform understands how to work with them. Because we can use any modeling framework such as XGBoost, PyTorch, CatBoost, JAX, anything we need in order to solve our problems, we need consistency in what the model is actually going to look like. And this is where we bring in CBML's base model class. Base model is an abstraction over the life cycle of a model where the ML engineer determines how the model will train, do predictions, and then how to analyze performance of the model, as well as loading the state. This allows us to use any Python-based ML framework without actually worrying about the implementation details. We can leave that entirely to our ML engineers. So now we've prototyped our model. We've checked in an instance of base model. We can train our model. We train our models using SageMaker, Amazon SageMaker's Bring Your Own Container framework for all training. All metadata and performance information is stored in Nostradamus, our control plane, and we require code to be reviewed before it can be used in production jobs. Only artifacts produced by production jobs can be deployed as model endpoints in our production cloud. This is our workflow for checking in models and achieving consensus. First, an ML engineer submits a PR to GitHub with their model code. It gets reviewed and then eventually approved by a peer, who then uses 2FA to form consensus. This triggers a build through our CodeFlow artifact builder, an internal tool that Coinbase has, that publishes a container along with the model name, the version of the code in the model, and the container tag to Nostradamus. And this is stored within Nostradamus' metadata. Now the ML engineer can start a training job. This creates a job instance using Bring Your Own Container and sets the job name equal to the tag. This tag will follow the model and the artifacts produced by that job for the rest of its lifecycle. The training job will run, returning configuration, metadata, and performance, and upon completion, will notify the ML engineer that the job is finished and they can deploy their job, the artifacts produced by their job, as an endpoint. So now we have production artifacts. We now deploy these artifacts as a Amazon SageMaker endpoint using the same container the model was trained in. Score requests are proxied through our centralized gateway, Nostradamus serving, where feature vectors are enriched by our feature store. Our feature store does aggregates over event streams and then publishes to Dynamo, which Nostradamus serving queries in order to enrich feature vectors with extra data before passing on requests to our endpoints. Again, the same base model class and training job container are used for both training and inference. This is a high-level overview of our feature store. Feature store allows streaming features using Flink via AWS EMR. We watch event streams from throughout Coinbase, powered by Amazon Kinesis, and then use Flink to perform streaming aggregates on those event streams. Features are computed off those streams and stored in DynamoDB for real-time inference, as well as emitted to S3 for training. We do online merging of features, of these batch features, and streaming features within Nostradamus serving. Finally, we roll out a model into an experiment. We have an in-house experimentation platform that we call Cypher that allows us to roll out model deployments in a 5, 10, 50, then 100% fashion. This means that we will always roll out multiple iterations of the same model at the same time with slightly different thresholds or hyperparameters or different settings so that we compare two models to the baseline of either the previous model or whatever the control happens to be. In summary, Coinbase needed to build a platform in order to detect fraud in real time. We chose AWS SageMaker because it provided our requirement for being secure with IAM permissions and bring your own container fitting our high security standards. Low latency, SageMaker endpoints are able to respond to real time and we can optimize our models to work within those SLAs. And then flexibility. Bring your own container gave us the freedom to use any modeling approach that we wanted and to optimize our model code in whatever way we found necessary. SageMaker endpoints allowed us to deploy quite literally any model that we wanted to because we could control what was in the container. And then our endpoints could be integrated with our feature store in order to enable cutting-edge sequence-based modeling techniques. Thanks for your time.
Thanks, Eric. Now, if you're excited about what you've just learned about how Coinbase used SageMaker to build their machine learning fraud systems, and you'd like to get started on doing that for your fraud use case, I will go over 2 fraud detection solutions built by the team at AWS that can help you get started quickly. These solutions have the components of a fraud solution already wired together, and they can be launched with just a few clicks so you can see how they work on public datasets. The first solution provides a good starting point for building and deploying fraud detection models when you have tabular data, with or without the actual fraud labels. And you want to deploy the model after it's trained to a real-time endpoint. Right, so at a high level, here's how the solution works. For model training, we use the SageMaker built-in algorithms to train both a supervised and an unsupervised model, and these are then deployed to SageMaker endpoints. Now, in production, in order for you to invoke the models for predictions, you can send a request containing features to an API gateway REST API. This REST API is backed by a routing Lambda function, which invokes one or both of the model endpoints to get predictions that are then returned back to the client. The routing Lambda also post-processes and saves all of the requests to an S3 bucket via Kinesis data firehose. The data in that bucket can then be consumed downstream for visualization or analysis. Now, to get started with this solution, check out the GitHub repo, which contains a template that you can use to launch all of the resources in the solution into your AWS account. In the second solution, we leverage interaction graphs. So graphs are an increasingly popular way of representing online interactions and transactions because of their convenience and flexibility. And graph neural networks, or GNNs, can be trained directly on graph data, as well as some features about users in order to classify users as potentially fraudulent or not. Right, so in this solution, we show how to use Deep Graph Library and Amazon SageMaker to train a custom graph neural network, or GNN model, for fraud detection. We use lambdas to automate the process, and then use SageMaker processing jobs to transform tabular data into graphs, and then a SageMaker training job to train the GNN model and generate the model's predictions. Since we can take advantage of links that the user has since we can take advantage of links that a new user has with with known fraudulent users, we can predict that a new user is fraudulent before the user has had any transactions or has even attempted any malicious activities. So like the previous solution, with this solution, you can find and launch the solution on GitHub in the repo that's shown here. And for fraud detection, both of these solutions offer ways for you to move quickly from concept to production with just a few clicks and tweaks. Thank you for listening, and happy building.